Is it over? No. Oh, for God's sake. No, it's not. Okay, I'll tell you what, if you're gonna do that, you need to like go outside somewhere where it's not here and we're not gonna make noise in the hallway. So maybe like outdoors, and then come back when you're ready and we'll start our lesson now. I am recording it, so if you miss it, that's okay. I'm not mad or anything, I just like, it's just disruptive, right? So it's fine. Okay, so here we are with our sp3 hybrids. This is where we left off last day. Yes? So we had a single s orbital and we had 3 p orbitals. Oh, by the way, I didn't ask if anyone has any questions about the test. Does anyone have any questions about the test? We are aware that there are Lewis structures and formal charges on the test. We are aware that there are those reactions of metals and nonmetals on the test. Yeah? Okay, good. All right. So this is not on the test. This is your next unit. And we are on page 25. Yay! Okay. So if you take... Are we all done? Yay! And I take it was a good ending? Yeah, okay, good. Go grab yourself one of those if you don't have one already. Add it to your red book. So, for unhybridized orbitals, an s orbital, a p orbital, a p orbital, a p orbital. For unhybridized orbitals, make how many hybridized orbitals? Yes? Yeah. So if I have 4 unhybridized orbitals, an s and a p x and a py and a pz, how many hybridized orbitals will I get out of that when I shake them up? 4. Okay? So you don't end up with any more or less orbitals than you had before. They've just all been shaken up in a blender so that they all have the same characteristic now, instead of being different from one another. And if you remember, when something is sp3 hybridized, that's 1 s and how many p's? 3 p's, and hence the sp3. What is the bond angle? 109.5. And what is the shape? Tetrahedral, yes. Okay, excellent. Now, so if I ask you about the electron domain geometry, that means an electron domain An electron domain is an area where electrons live. So an electron domain is an area where electrons live. And if we look at our hydrogen sulfide molecule, we have electrons living up at the top. Yes, up here. We have electrons living at this corner of the tetrahedron. We have electrons living in between the S and the H, right? There's a pair there. And we have at our other corner a pair of electrons. So we have pairs of electrons in each of these positions. So how many areas are there where we have electrons? 4. So we have how many electron domains? 4 electron domains. And anytime you have 4 electron domains, the electron domain shape will be tetrahedral, because that's how you can get all 4 electrons as far from one another as possible. Is good? Okay. So what is the electron domain geometry of H2S? It is tetrahedral because we have 4 electron domains. Now I'm just introducing this term now. We've actually got a whole section on it. Section 11.4 is all about molecular geometry. So don't worry about it just yet too much, but just to introduce it to you, if I was to ignore my 2 lone pairs, what would an H2S molecule look like? Like what shape would it be? Like if I were the S, where would the H's be? Like this, yes? Off it with an angle of 109.5 or thereabouts, okay? And this shape has an awesome name. It's called bent. Is that great? It's bent. Okay, so what we've got, the molecular geometry, we have S with an H and an H, and we have 109.5 degrees. We'll learn that it's not exactly 109.5, but we'll learn that later. It's still called bent. So what's the molecular geometry? Bent. Okay, here's methane. This is carbon. Now, in order to form methane, we need 4 H's to be attached, right? How many electron domains is that? H, 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 H. How many? 4. So we need to hybridize how many orbitals? 4. So here we have our 4 orbitals. We got 1, 2, 3, 4 orbitals. And we are going to, first of all, we say that we promote an electron. So we're going to take this electron and move it up here. Now, in reality, does this happen in like this weird little 2-step process? No, it just doesn't. I mean, all of a sudden you're like, bam! You're like, I've got my atomic orbitals like this, and then bam, I've got these hybrid orbitals, each of them which has a single electron in it. They're not bumped up so much as they are just all equivalentized. Equivalized? Equalized. Equivalentized. Yeah, they just all merge into one style of orbital, okay? And you'll notice that this sp3 orbital is lower in energy than the 2p. right? But it is higher in energy than the 2s. So it's sort of in the middle. Oh my God, what is wrong with me? I always answer the questions that I have before I get there. In terms of energy, how do the sp3 orbitals compare to the original 2s and 2p orbitals? Well, they're lower in energy than the 2p and they're higher in energy than the 2s. You don't need to write it twice. You can if you want to. You could answer this one though. How do the sp3 hybrid orbitals compare to each other in terms of energy? They are all the same or equal. What's the word that we use for that? Degenerate. What kind of bond, sigma or pi, do we get when carbon's sp3 orbitals and hydrogen's 1s orbitals overlap? That is our sigma. Yep. Sigma, 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 sigma. Here's a little weird one. In which of the following molecules is the central, that should say central atom, not molecule. In which of the following molecules is the central atom sp3 hybridized? Do we have an sp3 hybrid in PCl5? No, we do not, because there's not 4 electron domains, right? There's like, how many electron domains do we have here? 5 electron domains. Therefore, it is not sp3. In fact, in the past, we would have taught you that this is sp3d hybridized, but apparently that's wrong, so we don't teach it to you anymore. Okay? We just don't bother with hybridization after we get to 4 electron domains, and we stop talking about it. I don't know what they say instead of it, but they have not informed me, so there we are. Now, we have NH3, which has 1, 2, 3 hydrogens, and it has a lone pair. So how many electron domains does nitrogen have? 4 electron domains. So what is its hybridization? It is sp3. There's no 4. We don't put any numbers in front of the hybrid orbitals. They're just the letters. Yeah, it doesn't matter. We have 4 sp3 orbitals, but we just say that the nitrogen is sp3 hybridized. Okay. How about beryllium here? We have beryllium, H2, BeH2. How many electron domains do we have here? 2. There's 1 overlap here. There's 1 overlap here. What kind of overlap is this, sigma or pi? Sigma. We have 2 electron domains. Anyone want to guess what that shape is? Linear. Yeah. Okay, shape. Yeah. Linear and then bent. Those 2 are nice, and then we'll get into the weird ones like octahedral and trigonal planar and, you know, some weird ones like that. But yeah, I know. It's not very consistent, is it? So for a central atom to be sp3 hybridized, it must have how many electron domains? 4. Anyone want to take a guess as to the hybridization of BeH2? Yeah. That would mean it would have an S and two P's, which would give us just SP. Here's some other hybrid orbitals. This is the one with beryllium. Here is our orbital diagram for beryllium. 1s is full, 2s is full. In theory, could we form any bonds with this? It doesn't look very bondy, does it? No. But what we can do is we can take the 1s, it's a core, so leave the core alone. It's just the valence electrons that do this. We will promote one of the valence electrons. From the 2s to the 2p. Okay, up it goes. Now we have two unpaired electrons. Isn't that nice? This is where the 4 comes from. This is why BE doesn't follow the rules. All right, now this is lovely. So we have fixed a problem. We have fixed the problem of having no unpaired electrons for bonding. However, experiments show that the two bonds between beryllium and fluorine are identical. Is that possible if we have a 2s electron and a 2p electron? No, they would be different because the 2p would have different energy than the 2s. So how can we fix that? We can hybridize. Yes, indeed. Okay, so here's our s orbital. Here's our single p orbital. We're not using the other ones. The other two are just sitting there. Okay, we hybridize them, and because we have two orbitals here, unhybridized, we end up with two hybrid orbitals. And if we show them overlapping on each other, we are showing only the large lobes. If we showed the small lobes would go like that and like that. The sp or hybrid orbitals together, they look a bit like a p orbital, but the p orbital wouldn't have those extra small little lobes there, okay? One of the lobes is larger and more rounded, like an s orbital. Okay, so that's the s component of it, and one of them is sort of more like a p. So, using our orbital diagrams, we would hybridize it like this. We would take these two, a 2s and a 2p, and we would hybridize them into a sp hybrid. These two 2p's have been left alone. These are still p orbitals. What geometry is formed by an sp orbital? How many electron domains do we have in an sp orbital? Two electron domains. How is it possible for two electron domains to get as far from one another as possible? So what's the shape? Linear. And what's the bond angle? 180 degrees. Not this test. Not this test. But fortunately, linear is like super easy, right? You don't have to be like, oh, what's the angle? It's not like 109.5, which is a weird number, right? Like this one's like, oh, it's 180. Yeah. In terms of energy, how do the sp hybrid orbitals compare to the original 2s and 2p? They're in between. They are higher than the 2s. They're higher in energy than the 2s. But they're lower in energy than the 2p. Oh, and look what I've already done. I've already done draw a circle around the orbitals involved in the hybridization. There we are. Okay, we did that. How many s orbitals are involved? 1. How many p orbitals are involved? 1. How many unhybridized p orbitals remain? 2. How many sp orbitals are formed? 2. So we have 2 makes 2. That's left over. How many s orbitals are involved in sp3? 1. How many p orbitals? 3. How many sp3? This should have a 3 here. How many sp3 orbitals are formed by sp3 hybridization? 4. Got to put a star there. Fix. How many unhybridized p orbitals remain? 0. Okay, excellent. What are we missing so far? We've got sp3, we've got sp, we need sp2. Let's take a look. Here is boron trifluoride. Huh? What's our bond angle going to be here? That's 120. Okay. The geometry, there are 3 electron domains. We've got a bonding electrons here, here, and here. This is a triangle in a plane. Although I'm not sure you have how you would have a triangle that's not in a plane, but it is called trigonal planar. Trigonal planar. That's another one of the weird ones. We went from bent and linear. Wouldn't it make sense to like have triangle? But no, it's not triangle, it's trigonal planar. No. Yeah, I know, right? Sometimes people pronounce it trigonal planar. I'm not actually sure which one is correct. So pronounce it however you like. Okay. Do you think that the boron atom is sp hybridized, sp3 hybridized, or something else altogether? sp2. sp2. Let's predict what happens in the promotion and the hybridization. So who will get promoted here? The 2s electron will get promoted. So we still have our original one and our other one, and now we have the promoted one. Yes. Yes. Whoa, what happened? Is that good? Okay, but we're not allowed to do that anymore because it's wrong. It would be sp3d. That's what we used to learn back in the day. And it made me happy because it was like, oh, we just continue on with the process. And then if you had 6, it was sp3d2. But no more. Because physics. Somebody discovered it didn't work that way. And now we have to learn something else that's more confusing, but we don't have to learn it, so that's all right. Yeah. Somebody in 3rd or 4th year chemistry might have to learn it, but we don't. All right. What? We just stop at 4 hybridization, and the rest of them we don't worry about it. We just say this model does not work for hybridization. A hybridization model does not work above 4 electron domains. Yes. No, it does happen with other ones as well. We've been focusing on these because it makes your life a little bit easier, but we'll take a look at what happens with other ones in just a moment, okay? Now, how will we draw our hybridized orbitals here? How many should I have in my little block here? 3, right? Because I'm hybridizing 3 of them. So those 3 are going to become these 3. And they each have 1. What do we call those ones? sp2. Those are our sp2 orbitals. And is there anything left over? There's a 2p left over. Okay, I think we've done question F already. Ooh, what's that, sorry? Oh yeah, there's a 1s2. It's just not a valence electron, so we're ignoring it. Okay. What do we predict that the hybridized orbitals would look like? Try to draw each orbital separately and orient them properly. So give it a go. Try it. The orbitals involved in hybridization, there's a 2s, there's a 2p, and there's another 2p. Now you're going to draw the hybridized orbitals, what you think they will look like. Yes. We just don't worry about it. It is, but we just don't worry about it. Je ne sais pas. Yes. She asked, why don't we say 2sp2? And I said, we just don't worry about it. And she said, pourquoi? And I said, pourquoi pas? And I said, je ne sais pas. Because I do not know. No sé. I don't know how to say it in any other languages. Ik fai. Excellent. I'm going to forget that one, but I'll ask you again later and then I'll be reminded. What do they look like? What do you think? Each of them should have how many lobes? 2 lobes. So we might have one that goes like this. What would the other lobe look like? Small. Now, what direction should the next one point? At 120 degrees. So maybe it's like this. Oh, I did not draw that well. There's our second one. And what orientation would our third one be? So that's separate. That's all of them separate. And what would we get if we overlap them all? La la la. La la la. La la la. Those are all supposed to be the same. Maybe I'll get rid of this one and make it better because that was pretty terrible. And then we could have our little lobes there. And that, no, I'm going to leave out the little lobe. Oh, no. Ah, look at that. Okay. Okay. Now, sigma and pi bonding, which we have already talked about. So we're just going to look at all the various different possible sigma and pi. Sigma bonds can be caused by SS overlap, by SP overlap, by any hybrid orbital overlapping head-on with another hybrid orbital, a hybrid orbital overlapping with S, a P overlapping with P, a P overlapping with a D overlapping with a D, or a D overlapping with a D in this orientation. Whew. Those are all sigma bonds because they're all head-on. Sigma bonds, we got HH, which is SS. We've got HF, which is an SP overlap. We have PP overlap. That doesn't sound good. Anyway, that's fluorine. Here's some more examples of sigma bonding. We have the sp3 overlapping with an S. We have sp3 overlapping with S here, here, and here. And then the sp3, the fourth sp3 of one carbon overlaps with the sp3 of the other carbon. What would the Lewis structure for this thing look like? Just a C and a C, and then HHH, HHH, right? And what is the name of that thing? That is ethane. Oh, and look, here's our internuclear axis again. Our pi bonds are either between P and P, or P and D, or D and D, and you'll notice, oh, D and D. Okay. Anyway, D and D, yeah. Dungeons and Dragons overlap, okay? Now, let's take a look at ethene. How many electron domains does this carbon have? 9. 3. Because a double bond is all considered the same area. It's all to the right of the carbon. But they're all over here, right? I've got an H and an H. The H is here, the the other H is here, and then the carbon is like over here, right? So the sigma, I've got a sigma here, and then I got a pi above and a pi below, but it's all here, right? So it can't be tetrahedral because these two bonds have to orient each other along the internuclear axis. So we have one bond that's on the internuclear axis, one that's above and one that's below, but they're both like along the same line essentially, right? We've got one here. Here's our carbon. There's our sigma bond. Our pi bond would look like this. And where are the electrons relative to this carbon? They are to the right of the carbon. Okay, where are they relative to this carbon? They are to the left of that carbon. So that all counts as one area. Okay? And then you would have up here, you would have your hydrogen, your hydrogen, your hydrogen, and your hydrogen. Well, we only look at the total amount of domains for a single atom at a time. So we look at this carbon and we say there are 3 electron domains. Therefore, what is the hybridization of that carbon? It's sp2 hybridized. And the other carbon also has 3 electron domains. So the other carbon is also sp2 hybridized. And if we have sp2 hybridization, what is left over? The 2p orbital. And what overlaps to form pi bonds? P. So here's what we have. Okay, we have an sp3 orbital. We have an sp3 orbital, and we have an not sp3, what am I saying? What should it be? It should be sp2. So this is sp2. That's our first one, sp2, sp2. This one, sp2, sp2, sp2. But we also have unhybridized p orbitals. So when we bring them together, these guys are going to come together and overlap, and that's going to be our what kind of bond? That's going to be the sigma part of the bond. Now what's going to happen when we have the overlap here? That's going to be our pi overlap. Now remember, these two lobes together, they only make us like one pi bond, right? So we have a sigma bond, and we have a pi bond. Yes? So we would have, okay, some of the time the electrons would be up here. Some of the time they'd be down here. Some of the time one would be here and one would be here. And if you took photographs over time, you would end up with a density pattern that gives you those two lobes. Now, once again, How are they getting from one to the other? How are they moving between them? Are they teleporting? What are they doing? They're waves, and all of a sudden they condense to a single point, you know, and now we're back to hand waving again because that's well beyond the scope of this course. I would imagine you would be studying that if you were taking like upper level physics. Okay, probably not even upper level chemistry, I feel it would be upper level physics to do like what's actually going on in there. And I kind of scraped my way through first year physics by sheer hard work, and then I was like happy to see the back of it. I was like, yes, bye-bye physics. So I will not be the one to take you through this journey of how that actually happens. No, the electrons from the sigma bond stay in the sigma bond. The electrons in the pi bond stay in the pi bond. Yeah? But the electrons in the pi bond could be down in this lobe, or they could be up in this lobe, or one could be in each. But don't fret about it too much. You just need to know, where is the density for the sigma bond? Along the internuclear axis. Where is the density for the pi bond? Above and below, or in front and in back of the internuclear axis. Yes. Okay, yes, like a hot dog. Yes, ethene looks like a hot dog. Hang on a sec. Let me just, let's see if I can find one for ethine. Ethine Okay, so here is ethine. So you have, and I thought I had this in here, and I think I accidentally deleted it this time around. So we have the sigma bond. I feel like this isn't quite right. It should be like about, this one should be red and that one should be red. This one should be blue and that one should be blue. That's what I feel. I feel like this is a little bit wrong. Let's see if there's another one that's better. There we go. That's the one we want. It's a couch. So we have our sigma bond, which is in yellow. We have our first pi bond, which is in blue, and we have our second pi bond, which is in purple. Yeah. Okay. Now, are you going to have to draw this? No, you don't. Oh, it does look a bit like a water wheel or something like that. Yeah. Yeah. Clouds, we're looking at the clouds. Ooh, I see a dog. Ooh. Okay. Get rid of that and that. And there's nothing. Yes, sorry. Yep. Hang on. My mouse is just misbehaving for a moment. The one on the website? There. Okay, I cannot hear her. Shush. Yes. The 2p orbitals are what? There's only one 2p orbital unhybridized in each of them, yes. Yes, they have electrons in them. There's one electron in this one. Where did I put my pen? They have a single electron. So they pair up so that they have 2 electrons. Why would they become an sp3? If it became an sp3, then we couldn't have a double bond. And we do have a double bond. Yeah? I mean, it could become an sp3, but then you would have ethane instead of ethene, and it just is, they occur under different circumstances. Yeah? Nothing new here. This is just a summary of the simple shortcut. Okay? So you don't have to be like drawing llamas and anacondas. You don't have to be drawing orbital diagrams. You just look and you say, how many atoms and lone pairs are attached? That is the number of electron domains. And if you have 4 of them, you are sp3 hybridized. If you have 3 atoms and lone pairs attached, you are sp2 hybridized. If you have 2 atoms and lone pairs attached, you are sp hybridized. So here is carbon, and it has 1, 2, 3, 4 electron domains. Therefore, it is sp3, because there's an s, which is the 1, the p, which is the 3. 3 and 1 give you 4. Here I have a carbon, and it's only got 3 things attached to it. You'll notice it has a positive formal charge due to that. How many things are attached to that carbon? 3. So what's the hybridization? sp2. Here is a carbon. There is 1 atom attached, 2 atoms attached, 3 atoms attached. That gives us 3 electron domains, so it is sp2. Here is a carbon. It's attached to something else, the rest of the molecule, okay? And it is attached to a nitrogen. So what is its hybridization? sp. I think I went like little crazy on this because I feel like, do you guys already understand this? Yeah. So, I mean, you can take a look at this. You know what? Maybe next year, once you've forgotten it, you'll be like, ooh, I'm just going to take a little look at the shortcut, right? Okay. And you can be like, oh, I don't know what page this is. It's just after this diagram, 34, this one here. The only thing that's new on here is the word steric number. Steric number is just a way that we say the number of electron domains. Those two are the same, okay? Other than that, I don't think there's anything new here. If you want to get some practice, you can try these. Okay, I'll leave that for another day. Can we talk lattice energy? 11.2a, lattice energy. This is ionic bonding. Sorry to keep pushing, but you know, it's this big course, huge course. So this is on page 30 something. No, hang on, lattice energy is on page. Well, if you don't have lattice energy yet, then you need to come get one of these. And it is on page. What do you know about that page? How irritating. Well, you guys get one little break while I go and photocopy page 37B. I'll be back.
I'll pay $20 an hour and 24-hour training sessions. I thought you knew the formula of the way. No, we're going to training. I'll take my raise and I'll throw it right behind me.
I give up. It's jammed. So, how about if questions on the energetics of covalent bonding? Why don't you just do that for like pages 4 and 5? It'll be a little review of what you did. Just do pages 4 and 5. A review of what we did on Wednesday before it escapes your brain entirely. Pages 4 and 5. It's actually probably a pretty good idea anyway.
So what pages do you have? What pages? 4 for
Hey, you go in your numbers of pages.
no, I numbered it wrong.
Oh.
I put like 1. But then I stopped it.
Okay. Okay. Oh. Attached to that card. Is there anything else attached to the card? Please guess. It's like hybridization. It's just like, here, I give you no information. Please guess. Like, you can't, I can't do that. I have to be like, here's your compound. Please tell me what the hybridization is. Yeah? Yeah, yeah. Just depending on what you need. Yeah, that's how you do it. I'll make an exception because it's a Monday. I will answer questions during flex, but not at the end of flex. Okay? Ladies and gentlemen, because your test is on a Monday, which I don't enjoy doing, but you know, we have our issue with Tuesday, so that's okay. What I will do is I will answer questions during flex on Monday, but do not come at 9 o'clock for flex and like while I'm getting my grade lines ready and be like, oh, this guy, 10 minutes late. 8:20, 8:30. We'll have a nice calm conversation. It'll be nice. Yeah? You know what? I would love to send you home right this second. That would be awesome. But I'm legally obliged to keep you here.
I appreciate it more than you do.
You're welcome. You too. You're welcome. You too. Okay, what do I need to do? Hi, Gavin. How are you? Oh no.
Our car got stolen.
What?
In an apartment. But good thing is we made the report in a whole week.
No good.
Hopefully we got our vehicle back. I was so sure. Why would you
I
report?
hope you do. That's a terrible thing to have happen.
Well, 30% only get their car back.
Yeah.
That's a low number. But good thing is that we want police as soon as possible it happened.
Yeah.
And the officer is investigating the case.
Good.
Once we have a sign that we see the person who did that, if anyone knows the person who did it, report to police right away. We have the security footage now. I'm learning these things. That's a few.
This is all good. Okay. Now for IC value of 28.
I'm learning lattice energy.
Yeah. Yeah. So you're going to closer, right? So without a double one, it's actually better. Yes.
Yeah.
So you're like, okay, so I got my I, I got my CO, I got my CO, I'm like 26. Iodine
I
is
heard that a lot of students have had to do for
Oh,
like
for
a one class. I heard that there are a lot of failing students for their midterm. How do you know? Hey, you're right. I never seen the statistics across over me. I wanted to math.
Yes. And so this one is double one. Not sure where that is. Okay. And then for resonance, right, it's double one. This one's actually a little tricky. I share it, I can express it, I'm not going to be able to.
I remember this. This is for the meeting. On my final exam today, it was okay, but for the midterm or exam one, Daniel Levin, the professor, failed the exam, 47% of the class average, and Professor Jeff Moore and now the probably high school teachers failed you, that's what he said.
I found, and I will say that we are ready for the word on COVID.
Yeah.
So you only have learned the art of working on it.
Yeah, I didn't know this stuff, but I got above average. I don't know, honestly, yeah, but why would we not fail from Mars? Why would other people fail? And, yeah. Dude, it's four stops. No, but like, I'm not just one two pusher. Why not? She'll walk to the rest. I don't.
I tried to, but it didn't work, so we didn't worry about that. We just did the extra four instead. Yeah.
Last question.
Yeah.
And that one is like, it just overlaps. Why does it bother me? Does it bother you? Like, it's so high. I'm doing it for you. Okay. Your time has its natural state, yes? It's going to essentially attract the force to come back. Yes. So that's like what we're doing.
What's good?
Now, what if you press
Michaela, move to the office, please. Michaela, move to the office.